Hello all, I am Vinay. Today we are going to discuss about the calculation of 8-point DFT using the Radix-2 DAT FFT algorithm. Before going to the example, first let us discuss about the fast Fourier transform. FFT are the class of algorithms that are helpful in efficient and fast computation of the discrete Fourier transform and its inverse. FFT reduces the complexity of the DFT from the order of n square, which is by using the direct method, to the order of n log n, which we will get by using divide and conquer approach. Here and refers to the data size. FFT are very useful when the data size is in millions. The difference in speed of computing the DFT using the classical approach and by using the FFT algorithms is very significant in case of larger data sizes. FFT, DIT and DIF, decimation in time and decimation in frequency are the two ways of implementing the FFT algorithms. The FFT algorithms reduces the complexity of the underlying hardware and increases the computational speed. The complexity here is discussed in terms of number of additions. Subtraction is also same as addition and multiplication. The FFT algorithms inherently uses divide and conquer approach. The divide and conquer approach is based on the decomposition of endpoint DFT into successively smaller DFTs. The basic divide and conquer approach leads to the family of the efficient DFT computation algorithms, which we know as FFT algorithms. We can extend the divide and conquer approach to the radix algorithm. Here n is written as r power t, where r is the radix or base, t is the number of stages in the FFT algorithm, n is the input data sequence length. Radix-2 DAT-FFT algorithm. Radix-2 algorithm is a special case of Radix-R algorithm where R is equal to 2. Here n is written as 2 power 2 where radix is 2 and t is the number of stages in FFT algorithm. Each stage contains n by 2 butterfly structures. Here if n is not a power of 2 then we will zero pad to make it n as a power of 2. Suppose we have 7 samples then we will add 0 to make it a, in which case 8 is a power of 2. The name butterfly structure in case of Radix-2 comes from the fact that the basic structure for computing the two-point EFT is similar to the shape of a butterfly. Here, as we can see from the image, the Radix-2 algorithm divides the input sequence into pairs of two based upon whether the positions is even or odd. By following this, we will get bit reversal at the input stage. Here, as we can see, we got 8 points. Initially, the points were partitioned based on whether they are even or odd, as 0, 2, 4, 6 are even and 1, 3, 5, 7 are odd. And in case of even also, they get partitioned into even or odd based upon their positions, and 0 and 4 are at the odd positions, and 2 and 6 are at the even positions, and 1, 3, 5, 7 also 1 and 3, 1 and 5 are at the odd positions, and 3 and 7 are at the even positions, and they get further partition into even and odd bit reversal at the input stage. Here we have 0, then the binary form is triple zero. The binary bit reversal is also triple zero, and the reversal in form also remains the same. In case of 1, it is the binary form is double zero one, and bit reversal is 100, and the bit reversal form turns out to be 4. And in case of 2, it turns out to be 2, and in case of 3, it turns out to be 6, and similar in case of 7, it turns out to be 7. Let us consider an example where the input sequence x of n be 1, 2, 3, 4 and 1, 2, 3, 4. Double n power k is known as the twiddle factor, which is equal to exponential of minus 2 pi k by n. Here we can see the values of twiddle factor where n is equal to 8. Now coming to the example, the input indices are written in the form of bit reversal, and x of 0 and x of 4 as having the value 1, and x of 2 and x of 8 are having the values 3, x of 1 and x of 5 are having the 2 value 2, and x of 3 and x of 7 are having 4. The twiddle factor Wn power k here the k ranges from 0 to 2 by 2 minus 1, which is equal to 0 to 0. I mean, double 8 power 0 is 1. So the first stage is simple addition. 1 plus 1 is 2, and 1 minus 1 is 0, and 3 plus 3 is 6, and 3 minus 3 is 0. 2 plus 2 is 4, and 2 minus 2 is 0. 4 plus 4 is 8, and 4 minus 0. In case of second stage, the bit the 12 factor power k ranges from 0 to 4 by 2 minus 1, which is 1. W4 power 0 and W4 power 1 are the 12 factor values, and W4 power 1 is same as W8 power 2, which comes from the fact that Wn power k is same as W2n power 2k. And again, 2 plus 6 is 8, and 2 minus 6 is 4 here, and 0 plus 0 is 0, and 0 minus 0 is 0, and 4 plus 8 is 12, and 4 minus 8 is minus 4, and 0 plus 0 is 0, and 0 minus 0 is 0. Now coming to the last stage, here the 12 factor power k ranges from 0 to 8 by 2 minus 1, which is equal to 3. So k ranges from 0 to 3, and coming to the third stage, here 8 plus 12 is 20, and 8 minus 12 is minus 4, and 0 plus 0 is 0, and 0 minus 0 is 0, and minus 4 into minus j, which is equal to plus 4j minus 4, minus 4j into minus j, it is plus 4j, and into minus 1, it is minus 4j. Minus 4 is equal to minus 4 minus 4j, and 0 plus 0 is 0, and 0 minus 0 is 0. Thus we get the DFT of the input sequence f of n at the last node. We get the same output by computing with the help of MATLAB. As we can see, 20, 0, minus 4 plus minus 4i, 0, minus 4 plus 0i, 0, and minus 4 minus 4i, and 0 plus 0i. The number of computations required for FFT are less for a particular value of n, as you can see from the above table. The total number of complex multiplications will be n by 2 log n to the base 2, and the total number of complex additions will be n into log n. So, hence we can compute the DFT of the input sequence by using FFT by a much easier way. That's all. Thank you.